Okay, thank you for coming to the last lecture. So I'm going to do a fun lecture today to close the whole semester. So I really appreciate you show up because you'll be rewarded, hopefully, with some good news, some good message. Many of you may ask, this. In fact, the discussion happened during office hour as well, right? So graphical topic model is a very big topic. And also there are many other, new or old subjects and areas in machine learning, such as deep learning, such as, conventional theoretical machine learning. How to balance the depth and also the breadth, for the presentation is always a challenge for every teacher and also for every student. Especially, nowadays, because people are so much, reliant on many of the deep learning technique to solve real-world problems. There's always a demand to, say, dive very deep into some specific algorithms, or maybe to cover specific ways of using a technique to address your real needs. I really hear that. But on the other hand, technology come and go. And what to be remembered is always an interesting topic. In fact, these days people are already talking about some new techniques in the space of reinforcement learning and transfer learning, and maybe how to extend deep learning in other areas. So it will be never enough that you cover all these topics. So today I'm going to share with you why the class is designed in a way that at some point we dive deep into the theory, and at some point we cover quite broadly into different areas. Because my goal is to give you, a framework of the knowledge so that you can fill in many of the gaps and the details if you want, so that you can, become versatile and generic, in solving not just one problem, but hopefully many problems. So the topic is what I called, a more civil engineering perspective of AI. I don't know how you feel, in research community, there is always this dichotomy between the science and the engineer. I think these two sides don't really like each other. They try to push the other side to be, a inferior kind of practice. Here I want to also share with you my position about how to reconcile the engineering perspective and also the science or the theoretical perspective. We've covered a lot, maybe the whole semester, on the research and the science aspects. And today we're going to use this last lecture to see how it connects to engineering. And in my opinion, in fact, I think engineering is always above science. Okay, engineering is not about the fiddling and tweaking and massaging, and abusing a technique. It's an insult to the word engineering if you understand that as engineering. I think some scientists, some professors always say, yeah, tweaking those things, numbers, and I don't like it because these are trivial engineering. That's actually not true. These are not engineering. Okay, these are literally fiddling. Engineering is a very, very rigorous discipline which only happens when you already have the science all finished or at least well understood. Then engineering is about repeatability, reusability, generalization, and also guarantee and robustness. That's why we see, for example, civil engineering, which builds on mechanics. We saw chemical engineering, which builds on full knowledge of chemistry. We saw electrical engineering because you know the physics of electricity already, right? Why there isn't an AI engineering? But because AI is not a full developed science yet. We have all these unknowns. And that's why it becomes art. So I'm going to say a few words about how we might be able to push AI into really, engineering in a real sense. And what we covered in the whole semester is kind of reflecting that kind of mindset that eventually we're going to use them as building blocks, okay, to do bigger things. All right, so let's see, how can we move forward? So it turns, people feels like we are in the AI era already, right? So we have all this amazing, display of certain AI, demos. I would say demos. I wouldn't call them capabilities, because capabilities means that we should all have it. I guess you cannot just implement or buy a piece of AlphaGo onto your laptop and play, right? You have to basically rely on someone, who claim they can play. And really the performance is great. You see all these robotic, innovations and, high, very, very high dimensional classification on image and play all sorts of game and so forth. But if you turn your head to what meant to be the consumer of AI, say, industries of all kinds, and when you ask their CEOs, this is a survey done by McKinsey, and in the CEO survey, most of them actually feel that AI is not ready in their own enterprise. They basically argue the following: there is a talent shortage, and there is a technology immaturity, reflected in the following two aspects. First of all, even if I need AI, I'm convinced that I really want to use it. I cannot build it in-house because either I cannot really have the culture or the resource to grow a team of PhDs and professors. That's how they understood AI should be built, and also there are other cost issue like equipment, infrastructure, environment, and so forth. Therefore, building AI in-house is not available. This is pretty natural. If something becomes mature, you don't build it in-house. You don't build an electric power plant in your factory, right? You just plug in some wire. That's it. And also, you cannot buy it. And if something is really mature, you should be able to pay for it and buy a piece back home and install it, just like you do with your TV set or your Microsoft Office. And AI is not a software, nor a hardware, nor anything that you can purchase. That kind of reflects the reality of AI, how people outside of the field see it. Why that happens? Well, there are many reasons. I guess this might be one reason. Many of the AIs, this is actually an article I cropped it from LinkedIn, and right after this year's big Google convention to show off a conversational function claimed to be built by their internal AI engine. And turns out the whole thing was staged. It was not even a real thing. Okay. That actually is one of the reasons many AI researchers are not serious about shipping a product that is meant to be robust and off the hands and in users' hands. The most that the story can be told is that, yeah, I'm a cloud, you come to me, and I'm going to give you AI because I'm in control. But you cannot extend your cloud to the Mars, to the moon, right? So, and many other industries are not ready to do that. They want a piece of thing in-house and out of your control, and they may want to even abuse it and manipulate it. And right now, I don't think AI is meant for that kind of shipment. It's meant for crazy, amazing demos. Okay? In fact, the AlphaGo play is a demo, right? And if I want to really, really challenge it, I change the board game, I change the rule, then the whole system is going to crash or it's not going to work. And likewise, many of the image functions, many of the text functions, in reality are closer to a demo than a real product. I tell you one story. I traveled to a country where, you know what that country is, right? There are cameras and facial recognition things all over the place. And I'm always suspicious about the real power of that function. So in one of the hotels I checked in, which is not a security desk, where the reception wasn't so forceful, I turned my back to the camera. Okay, and they were not asking me just to turn my face around. And the camera still passed me, say, hey, you are passed. Okay, so, I was trying to test out that system, how good it is, and I was able to come to a realization that the system isn't really working the way it was working. But anyway, so you can see there are a lot of gaps, in the claimed function of AI and in how they deliver. Not long, difficult functions like this. I said earlier that many of the real needs in data-intensive areas, such as in radiology, is more than just a classification label or a trivial tagging of the image. The real tasks are more close to how humans perceive and describe problems, such as in radiology, you generate a report that is digestible by the patient or by the next doctor, and the report generation is a very tedious and also needy work. We actually had a team in my group worked out this whole thing after a lot of efforts. And this whole system is actually quite complicated. It is not just a classifier or a so-called end-to-end deep learning system. You can see even from the high-level architecture, you can see already that there are first some embedding and some content to vec type of manipulation, so that you need to turn the image information into some representation in the vector space. And likewise, you do the same for the text. And then you need to really clean up the feature to get them aligned, because you are working on multimodal, bimodal data, image and text. Then you may build a co-attention model so that they can point to each other and make sense and also cross-enhance each other. And then you need to start understand the content and then produce a report. The report is an article that has both syntactic coherence and also semantic meaning. And then you need to generate all this content at word level, sentence level, paragraph level, and so forth. Therefore, in this case, you may use all different granularity of LSTM, but also you may call GAN models or maybe VAE models, or variations of that. So this whole thing is not end-to-end. You have to really tune and design and train separately each of that and put them together with correct interface. And then you are also not supposed to run this whole thing on your laptop, because it has to go to a hospital and build on the system. Therefore, there are all these encapsulations of the whole product into a way that is maintainable, that is upgradable, right? That is pluggable. And with that, you should ask whether the so-called auto ML is really a way to go. Are this whole thing automatable? Humans should be taken out of the loop and let the whole machine to come up with this whole design and also the implementation? This is actually not possible. Automating the automation is not automatable, basically. We are talking about auto ML is kind of misleading people to a direction where they thought people should not even write code. But that's not going to happen, at least in the way in the problem that we see. That's not even the whole story. You need to also plug in your software into an existing piece of a software ecosystem, which contain databases, which contain other programs in the run, and so forth. And all these different programs may be written in other languages, in different languages. Even in the space of machine learning, people already may be using, either PyTorch or TensorFlow or other type of new languages, right? So how they coexist? Do you want to just lock a subset of machines away and run only one program or not? Right. So interoperability is one other challenge. So this whole thing is basically part of an AI solution, and that basically makes the creation really hard. And how people do it right now, I think this is how people do it. It's no different from the a art master crafting a piece of, art piece, right? You craft and you chip and you polish, you fine tune and all that. And at the end of the day, you ship out a very delicate thing that is not supposed to be perturbed, to be interfered, to be fiddled with. And that's why, the users are not very happy. First of all, they are very expensive. They are not repeatable. And also they are probably not upgradable. A new algorithm come in may lead to the whole system to be re-implemented and all that. This is very different from how engineers see production, okay, in the engineering world, like a aircraft. First of all, an aircraft is following a very rigorous blueprint that specifies all the details in a highly robust and repeatable way. And also the production is in parallel, and the test was also in parallel. You test the engine differently from you test the body, and also test all the the dashboards and all that, right? It's not that you test that only once. When you assemble everything, you fly it. That's usually the last stage of the test. Before that, you do many things. So it's not an end-to-end black box engineering work. So now we ask, how can we actually advance or upgrade the practice of AI, engineering into this style, right? So that basically turns to a different question. We really need to build a mindset of the builders, which need to build, understand, and sustain the production. And here are all the potential nuance or requirements that a builder needs to take into account. For example, you need to really allow the solution to be reused and standardized so that another builder can build the same thing as long as he follows the same protocol. It should also satisfy the client-specified condition rather than your condition. And there are many other things as well, right? So that basically, is what is not very often discussed in our AI research, which are the trivial nuts and bolts and the workbench of AI. You want to really think, at a different level of granularity and quality measure, not just the performance curve, on how much you beat your opponent on the benchmark. And that probably could, open up, a new opportunity to maybe advance AI. So, which is very different from most of the content we talk about in this lecture, and also maybe in every university, right? So here we focus on reusability, standards, and comprehensiveness, rather than a very niche and one-off and specific technology. So with that in mind, I would like to again summarize a few key issues that enable such a transformation, and that also leads back to how we present and design this class, which hopefully fill in some of the needs listed in here. Every good engineering has to base on very good, strong first principle. Therefore, the theory is the foremost foundational work you have to do. But after that, you need to have a few other entries. So let's talk about the first principle first, because that's pretty much how we already covered the class, and we just want to do a good review to see how to tie them together, why we need to know that many, and also how to know even more. In fact, for example, how to remember, say, 5,000 different algorithms. Impossible, right? You just cannot remember all of that. But if you have a nice, say, if you go to the good old library, there are, systems for you to index and store and sort all different volumes of book. Therefore, finding knowledges when you need it should be quick, and assembling it hopefully should be easy. That's basically how we, want to see the technique in machine learning organized. And that again, presents you an alternative to the so-called end-to-end black box approach, because a black box is a one-off thing that is not decomposable. Therefore, it is very hard for you to reuse parts of that and for other purposes. So these are maybe examples of the black boxes, but how a principled machine learning process look like. Well, to a less organized person, it looks like this. It's a whole board of equations and numbers and all that. If you are still at this stage, I urge you to clean up a little bit and start building a bookshelf like this, right? All machine learning functions, and including the deep learning, the fancier, the modern one, really are built on a few key ingredients, such as the choice of a proper loss function, the structure of the model, which is mainly the major idea inside the graphical models. You are talking about structures between random variables, constraints, and then, of course, a algorithm, maybe even a workhorse or driver algorithm that works for many things, or a specific algorithm that's meant for high performance. And then you also need to determine the stopping criteria, how to stop. There may be a few more items, but these 5 should largely dictate how your machine learning creation look like. And then within each of them, there are many, many little choices that you can make, right? So for example, let's take this very trivial classification example. We know this very well. You first, you start with the data, and you build a classifier using, say, logistic regression in this case, or maybe a mixture of Gaussian classifier. And then with that, you can start asking a number of, worry about number of principles, especially in the theory side. You have bounds and guarantee sample complexity and all that. That's actually the beauty of starting from first principle, because you could characterize the behavior and also add more enhancements in a very, very informed way. And then there are more principles at your disposal to enhance it. You can do loss augmentation by introducing priors, by introducing regularizers, right? And Bayesian prior is one of this technique, but you can also introduce arbitrary regularizers as a vehicle to ingest human prior knowledges. And then you are going to be able to design powerful inference algorithms. And here this is just an example of how to turn model learning into a variational formulation, so that you can resort to very, very nice gradient or coordinate descent type of approach, which are more generic than a specific inference technique. And why these are good? Because when you have all these principles on the model design, on the algorithm, and on the augmentation, it helps you really to demystify and unify many, many existing models. I think in one of our lectures over deep generative models, myself and Zhiting probably present you a way to unify GAN models, VAE models, wake sleep algorithms, and all that into a single principle and allow new combinations to be brought in. For example, for a VAE model, you can still introduce a adversarial loss function, so that you can introduce more constraints, on the quality of the output. Even for the GAN model, you can also put a likelihood-based type of loss, so that you allow a certain type of data distribution to be estimated and to be reflected, and so forth. Right. So with all this, that really try to drive you into a way of thinking that builds on principles and structures, and then tie many, many of the instances and artifacts under a unified framework. And then with that, you can really start thinking about driver algorithms with good guarantees. And also the model usually can be designed in such a way that it avoids overfitting. You are not really coming up with a one-off model that is highly good at doing one job, but very poorly on other job, or maybe even on other data sets. Right. So that's basically how I want to steer basically hopefully your mindset and also the future work toward. So let's again turn back to the real example and see how we could put them into practice. So this is the example again, and I think it's really quite generic and hopefully also enlightening, because even from the very beginning at the task end, it is already combining computer vision, NLP, and and deep learning and traditional machine learning all in the same paradigm in order to come up with a legitimate solution. And also the task in here is not so dictated by trivial overplayed and overfitted benchmarks, which means that I tag an image or label an image. Report generation is a more kind of humanoid kind of function that is focusing on the usability rather than in winning a game. Here, you may ask how to test it, how to validate it. Yeah, in fact, people don't agree on how to test it yet. There are many different ways of testing them, such as testing on the quality of the language, the amount of facts you identified, readability of the whole thing, many, many dimensions. But no one disagrees that this is a very useful thing that they will use. Rather than uncertain classification, everybody agrees that the test is great, but no one wants to use it. Right. So that case, we give you, a mindset. Do you want to go for publishing a paper that builds on everybody agrees test benchmark, but no one end up using it? Or you basically go for utility, and then let the users to define, even in a more open space, how to validate. So I just explained this pipeline already, which includes even in this little diagram already maybe 10 models and 10 different algorithms. And I said, typically, including ourselves, our first version is like this. It's a highly crafted solution that you just put all the ingredients onto a platform, and which barely maybe work together, which actually eventually work together, but very brittle. That's actually a piece of production like this. You cannot sell too many copies of this. Not even maybe one is even hard to maintain, right? And the amount of work is very, very heavy. So with that, we turn to the process of how to do the civil engineering, how to, for example, allow us to do many copies of what we have. So civil engineering is about process and proper granularities of work units and the functions, and also how to maintain quality, right? So this build really entails a lot of things in the engineering world, many of which are not appreciated enough as of now in AI research, is at least. So I want to say a few words about some of these key dimensions, especially the nuts and bolts, and also the process. So let's take a machine learning program as an example. So this is a typical generic form of a machine learning program, right? So this loss function, depending on how you specify it, leads you to different models and different structures. And we have the parameters, and we have the data. And a typical driver algorithm is a gradient algorithm which updates the parameters based on some function. For example, a gradient of the parameters over the function, which can be computed from a data set. This particular term actually includes almost the holy grail of how to practice machine learning, because from both mathematical and from both implementational side, doing it efficiently and correctly is basically what a machine learning function has to achieve. So let's see how we may gradually, systematically update it. First from a machine learning researcher point of view. But again, even in this direction, I'm already presenting it in a step-by-step modular thinking, so that you don't really try to build a black box of end-to-end mixture or intransparent entity. For example, you may ask how to derive this particular function in light of different ways of regularizing. So remember, this R function, which is the regularizer, in fact, is one of the major weapons researchers use to empower a model. Right? In the old days, people use sparsity, and then there are group sparsity. there are fusion lasso, there are now diversity promoting regularizers, and there are many, many other things. And how to actually imagine a generic technique to produce this kind of the gradient under this kind of constraint. One technique is to not working on the algebra anymore. You basically are going to resort to a technique called the proximal mapping, that you treat every of this regularizer as a constraint space, and you're going to derive your unconstrained gradient first, and then make a projection. Okay, this is the unconstrained gradient, and you're going to make a projection into that space as almost like a robotic mechanical operation that you can build in any program. And then the constraint basically becomes a subroutine you call to define the space of the projection. That's one way of implementing your loss augmented gradient descent instead of a whole implementation that has everything in the same program. You may also want to accelerate the algorithm, because sometimes people find that built on the proximal gradient, you have a less than ideal convergence rate. And if some recent study has turned out that if you allow a momentum to be included in update, and then you can in many cases turn the convergence rate to a quadratic of the time. And how to do that? Well, all you need to do is to now remember two histories of the past updates. Okay, and then you're going to do a manipulation, a subtraction plus some reweighting to combine with the latest updates. So this is a very, very standard operation that can be applied to any type of proximal gradient. Again, that leads to a particular line in the implementation which really treat the acceleration step as a generic manipulation of two-step storage of the past updates. If you have a function that is difficult and not allowing you to derive your, say, gradient very easily, say it is non-smooth. So now we are talking about the loss function itself to be problematic. You can also do something. You can use something called a Monroe envelope, which actually allows a smooth coverage of the non-smooth function, and then you derive the gradient over that. And this envelope function can also be treated as a plug-in, okay, to augment your designed loss function. And lastly, if your gradient is so big and your data is so huge that you want to do data parallel or even model parallel algorithm, as we discussed in last lecture, there are, again, parameter servers and other technique for you to allow a plug-in realization of data parallel distributed updates. So I talked a lot about all these techniques already, which already gives you different dimensions of expanding this function. But they each themselves is not defining the full of a machine learning capability, right? So you are really in the state of having this pile of nuts and bolts, which seems to be very, very random and disorganized. And the purpose of this class, and maybe down the road, what you can do is to turn them into a very ordered list of nuts and bolts, so that you can systematically pick each of them and then make the combination. So this is very much like in a airplane or in a car manufacturing factory. The nuts and bolts are not of infinite assortment. It's actually quite limited in terms of number. They are reused in tying together different parts of the production, and also people know where to use what, right? This is very different from many in-house and artisanal way of building machine functions, where we either re-implement or we just arbitrarily define the program structure or the subroutine structure. So talking about nuts and bolts, again, they can be categorized into maybe a different stage of the machine learning needs. First of all, there is a huge need for just clean and wrangling the data. And this is actually sometimes known as a pre-machine learning step. And then within machine learning, you have all the modeling and the algorithm challenge. And then after that, you have the system harmonization. And here are just examples, right? Data wrangling, you have all these different ways of, say, projecting data. And you have different ways of computing transformations and the embeddings, and maybe even missing value imputation. These are like little units in the closet where you can throw in varieties of instances. But once you organize in this way, you can imagine that getting them selected and assembled should be a lot easier. And then machine learning, we have really, we could store a family of different loss functions and order the family of different regularizers in the terms of different shape of the space, and maybe a number of different driver algorithms, such as a gradient algorithm, such as MCMC sampling algorithm, and so forth. And then even on the system level, there are parameter servers and a number of other newer infrastructure and architect that can use to run the algorithm. So at the end of the day, what you may run into is a collection like this, where on data and on machine learning and on system, you can divide them into different steps. Okay, and then within every step, you have these little features that gives you very, very comprehensively, the options that you may have. So people may say that this is, scary, and this is maybe intimidating. These are so many. That actually is, unfortunately, a pathetic mindset in machine learning. We seem to be, on the one hand, we feel like we are powerful and we want to go to the moon and we do a lot of crazy things. But when we hear that there are maybe 100 or 300 parts, we feel intimidated. If you go to, a aircraft building factory or even a car factory, engineers and product managers are not afraid of managing 1 million parts. They are just assorted and organized and produced all different. That's why there are supply chain ideas, in other industry. Different parts, are produced in different parts of the world, and they got even purchased from different vendors, and then come and together and get assembled. That's how iPhone was so, not so expensive. Hopefully, the iPhone was giving a big profit to Apple. That's because they were able to buy parts cheap and sell it expensive, right? So in machine learning, we don't have this concept of supply chain of parts and nuts and bolts, right? And I did this graph myself. I literally counted how many parts that we need to provide in order to support, say, 95% of the machine workflow. It's not over 1,000. It's not even 500. You actually can literally count it. In the future, when you are going to a machine learning company, say, and wanting to build such a thing, you may always challenged by your boss and say, hey, data wrangling is so difficult. There are infinite ways of dealing with data. And so there are always this kind of urban legend and a kind of a mysterious claim, infinite ways of dealing with data, infinitely complex, so forth. I encourage you to sit down with him and say, hey, please name your way of dealing with your data. Okay, let's name it. And you may want to first agree on, let's decide what data to use. Are your data text or image? Say text. Then you say, okay, great, text. How many type of text you ever run into in your life? Name it. You will find that he will probably stop after 5 or 6. He will definitely stop after 30. Okay, and after 30, it's very hard to name a 31st different type of text that you run into. You have HTML, you have a blog data, you have a social media tweaks and other things. It's finite. And then you can ask, okay, with all these 30 type of data, how many ways you are going to clean it? No more than 10, I guess. And then how many different ways you are going to embed it and extract features. You do PCA, you do CNN embedding, you do word-to-vec, you do LDA, topic model, LSI. You just name all of that. Again, roughly a dozen, not too many. So when you do this type of a very, very careful interrogation to really figure out the ingestion, cleaning, feature engineering, embedding, and the integration, in each of these, you won't run into too many. Very rarely I can scratch my head and ask my engineers and colleagues to, collect more than 30 entries in that. Okay, and then imagine that this whole chart, every place you have 30 entries, how many in total you have? Right. So that's the point. If you take a very systematic engineering approach to a seemingly complex problem, it is not manageable. It's manageable, but you need to be very diligent and work it out. And you just build every parts and then categorize them. The key is to follow a standard and follow a quality control and also an interface so that they can come together at the end of the day. That's how in other parts of the manufacturing engineering people are adopting. They actually, even though they are in different parts of the world and producing different parts, they follow a common standard. And therefore, at the end of the day, things can be purchased and ordered and go together. And that's where interoperability becomes important. There should be a lot of collaborations between different teams and different people to make sure that your regression plug into other people's data ingestion function and other people's recognition function downstream, so that another one don't have to re-implement a regression function. Process is also important. Maybe we are still in shortage of a workbench, just like an assembly factory. Things can come together and gets assembled and tuned separately and tuned together and tuned by subsets of parts or as a whole and so forth. And this, at least in principle, can be figured out and implemented, such as through a graphical interface that the people drag and play, like doing the Lego, for example. Right. And then with that, soundness can be established, because soundness of a black box with so many different things really gets you nowhere. But if you have explicit parts for both data, machine learning assistant, you actually can establish guarantees and proofs for each of that. Right? You can, for example, establish identifiability on embedding. That's a pretty common thing people do. You can also establish a data complexity and convergence error bounds for a machine learning predictive function. And then you can also establish guarantees on distributed systems where you have latencies and data dropping and so forth. Right? And then you can put them together to provide an overarching guarantee. So I want to use text as an example to give you at least a hope. What I just talked about is not impossible. It's not like a fantasy that I'm just bragging about how much I know. It's actually doable. Did Chiting cover text in one of his early lectures at all? He did, right? So you probably know that already, right? So this is a project did by one PhD student, Chiting, as a leader, and another 5 or 6, amateur, part-time contributor in our department, no payment. And within a year, they can go that far already. It's a highly structured, pile up of the text-related toolboxes using the principles that I just talked about. As we all know, there are all these different tasks, in text generation. A combination of each will lead to a new task. It makes you feel hopelessly complicated if you want to cover all of that, right? And as Chiting probably told you, one way to do that is to really start sorting all these different techniques in the model and in the optimization and algorithm side, and start looking into the very structure of a solution, and then define what we know as the most common denominators, the building blocks that can be maintained as a undivisible unit, but still not too complex. For example, here we're talking about a time series language model, okay, a Markov language model. And then you can imagine different, again, in the simplest case, it could be just a HMM, one single state. But more complexly, every node can be replaced by a little LSTM so that they produce more dependencies and more complex structures. If you want to have a condition on other data, they can basically add additional context. And the whole thing in here, the model itself can be viewed as a decoder, and then the context can be modeled by an encoder. And then by this formulation, you can replace the encoder with a good range of different choices and plug in, right? And of course, you can also change the loss function from likelihood to be adversarial, and then as a result, you need to change some of the arithmetic choices of the functional form so that they can still be differentiable and so forth. And you can even introduce additional processes such as a reinforcement type of process, so that your data sampling and your evaluation becomes a closed loop that allows you to continuously train, right? So this whole idea is built on the modularization and the composability of the model. The model are to be composed from building blocks rather than built from scratch every time, okay, either using TensorFlow or other things. So as a result, they were able to really turn this whole mass of nuts and bolts into a highly organized set of building blocks, which is organized as a stack like this. There are high-level applications which are listed, for example, in my first page. And then there are libraries of APIs and config files. And below that, you have different stages of needs like training and evaluation, prediction. And then the model library contains different models. But again, it's not just a collection of built models. The models themselves are now designed and divided into the architecture units, the loss units, so that you can combine different architecture with different loss functions, right? And then in the architecture, you have all these different choices. In the loss, you have all this. So you can see this way allows you to really make, in a sense, infinite combinations of new innovations out of it, even based on existing building blocks. And therefore, you get really a model catalog that allows you to very easily and systematically build things in a very quick fashion. I omit one slide where they show that the same model using a TensorFlow type of language, building from scratch will take thousands of lines of code, but in here merely a few dozen lines of code because everything has been pre-made. Right? You actually all need to do is to assemble them. So this is what I see to be a promising future of doing machine learning. Instead of doing this, okay, you do this. You really compose rather than craft or write from scratch, even for very complicated functions. Okay, so that's basically an example of how the first principle in machine learning can lead you to a highly structured and organized way of instantiating new models, like what a civil engineer would do in their practice of making buildings and doing other stuff. I want to also take this chance to open up a few new topics so that you may take on to bring them into your own work down the road or just for fun. Because by viewing the machine learning and the AI and the graphic model in the way I just presented, actually opens up the interface to many, many other both engineering and the research intense angles. Some of you may heard this word SysML already, right? Have you heard about it already? This year, actually, we have the first international conference of SysML in Stanford. Last year, it was a workshop. It was a new field, promoted by a couple of researchers in the field, such as Jeff Dean himself. And in CMU, we have Garth Gibson, Greg Unger, myself, heavily involved in this type of research, which is to really promote the co-design of a system and algorithm. This is like, if you know what goods you are going to carry, you need to design your cart in a certain way so that they become more efficient. And then you have the interplay between them. And SysML actually covers many topics, including how to do auto-tuning, for example, how to do meta-learning, how to do learn-to-learn. But one particular area that that is really generating a huge impact is the distributed machine learning. Now viewed as an infrastructure study. It answers the following question. In fact, these are seemingly very trivial questions, but they actually inspired a lot of new research work. How to distribute, how to basically allow your message to be dispatched into different workers in a distributed setting, how to bridge between the worker and the master. And in fact, even what to communicate could be an interesting question. It's not as trivial as just communicate whatever you need to communicate. There could be surrogates or approximations or reductions to that. And also how to communicate, using what topology, using a round ribbon, using a star topology, master slave, or use a peer-to-peer broadcast. Right. So all this actually is becoming very interesting when you are implementing machine learning algorithms. So here I want to just say a few words about it. Did people see this graph from Qirong's lecture last time? Right. So this is the figure describing a new architect called parameter server. It was designed for solving estimation problems for larger models and bigger data where you need to compute the updates of the parameter based on data stored on different worker machines in a cluster because they are just too big. And then you need to aggregate and update and do it iteratively, right? And the interface of parameter server is just like maybe a single machine type of system. Although the underlying mechanism can be encapsulated. This is like the map reduce analog where you do a map dispatch job and you reduce to a master, but behind that there are specific ways of programming how to pass and receive communication and so forth. So in this case, the parameter server allows some particular type of style and principles to be adopted to make the message passing more efficient. For example, one of the idea that was invented here is this SSP bridging model. You probably heard that already from last lecture, which is to allow a partial asynchronous dispatch of the model parameters to different slaves in an asynchronous fashion so that they don't have to waste time waiting for each other. But it is not unbounded asynchronous so that the correctness guarantee is still preserved. So I don't want to spend time to describe the details in here, but because it is a very informed and rigorous design with all the parts being taken into account in the analysis, one can actually prove a theorem which actually guarantees the rate of convergence and also the condition of convergence of the distributed answer versus the serial answer, which is, of course, the reference point of the correct answer, right? So these two parameters actually was playing a very interesting role. One is the median, the average of the delay between all different workers in a cluster. And this one, theta, is the variance of the delay between different workers. So you can imagine that these two numbers can actually be controlled by an operator, right? You can, for example, set the threshold of SSP to be 10 iterations or 100 iterations to change basically this average delay. You can also implement either a push operator or a pull operator. Either you just send out and care less, or you actively grab message from every class, every worker for computing your aggregation. These two approach will affect the variance of the delay between different workers. So why they are interesting? Because your analysis now depends not only on the assumption of the data and also the assumption on the smoothness of the function. It also depends on the assumption of the behavior of the system. So this theorem, which was the first of its kind when published in 2013, was the first theorem in machine learning which contains parameters of the system. Imagine it's very interesting, right? You analyze machine learning algorithms, proof theorems so much, so often, but the only parameters in that are usually the smoothness of the function and the divergence of the properties of the data. You don't actually care how the algorithm is running on a real machine. And that type of theorem in practice is not very useful because your machine can behave in many different strange ways. And here you actually are now bringing those additional system parameters into the analysis. That's actually why when you think about AI to be a real workhorse in a scenario on the system, change your mindset in many of the analysis. So I want to go a little bit further and maybe talk another small topic on what's the alternative of a parameter server, right? Parameter server has been the dominant infrastructure and architect for most, if not all, the bigger machine learning systems nowadays. There are some systems. I think the Uber one is based on a MPI protocol, but that's a very complicated system which is very, very effective. It's very efficient, but it is not very generic in carrying different type of functions and models. But it turns out that the parameter server, architecture has some flaws, which could still cause very, very inefficient, operation. One of the flaws is that it really assumes that this delta W and the W, which are the parameters, are directly the entity to be communicated in the network. Okay, and that's very natural. I'm learning parameters, therefore, of course, I need to pass either the parameter itself or the delta of the parameters, right? That's very natural. But what if you have a very, very large model? Say nowadays, many large deep learning models can have a parameter, I think here, of the size of a few, say, a few billion bytes. Imagine sending the message of this size into the network and sending to, say, 100 neighbors. Your network will be choked by these big messages, right? So alternatively, there recently has been another idea which is built on the sufficient factors or sufficient vectors, which is not sending the W, but the low rank components of the W, which are known as the sufficient vectors. Okay, these are the mu's and the v's in here. They are two vectors rather than the huge matrix of parameters. And they must be sent not in a master-slave fashion, but in a peer-to-peer, broadcast fashion. So there is this very interesting trade-off between the direct size of the model versus the size of the network. And you can basically make choices to see which one is smaller to allow your network communication to be more efficient. So why this is working? Well, this is working only because you know enough machine learning and know that this is a legitimate message to send. And that's why this idea is not invented by the system folks, because they are not aware of such an opportunity in machine learning. That's why you guys should be the designer of the system in many cases. So these type of models are known as a matrix parameterized model. In fact, that's a pretty common type of model that we run into every day, such as topic models and deep neural network models, where the parameters is a big matrix of numbers. It turns out that the so-called full updates, which is in the form of a huge matrix, can actually be expressed in many cases by an outer product of two sufficient vectors. Okay, so your matrix actually has a rank 1 approximation that can be, you can really decompose them into an outer product of two vectors. Then if you make the outer product, then you actually have your matrix in your hand, and then you have to start distribute it and compute the gradient of that. But if you are willing to stay before that and only worry about the pre-update vectors, you actually could deal with two much smaller vectors and let them to be the message passed in the network. So that's the basic idea, within the sufficient vectors or sufficient vectors. And in this paper, there is an in-depth analysis of the correctness of this approach. When you are broadcasting them into the network in a peer-to-peer fashion. In fact, you don't have to really do faithful full peer-to-peer. You only need to send them to a few nearest neighbors, and then you just keep doing that because it is an iterative algorithm. The neighbors in the next iteration will be passing his message to the next neighbor. Eventually, all your messages will be populated in the whole graph. You will still get hopefully an intuition that the consistency is guaranteed, which is actually proven by here. It says that the result you get from that protocol is identical under certain condition to the full matrix communication. So as a result, you have another opportunity now to speed up, and here there is a comparison, for multitask regression, for metric learning, for sparse coding, which is a type of topic model, over the PS model, the sufficient factor model, and the Spark, which is a map-reduce model, and so forth. And you can see a huge advantage, in the efficiency, speed of the convergence. Okay, and also, in fact, it turns out that this idea about the PS and the sufficient factor can be combined. You don't have to, commit to only sufficient factor or only parameter server when you are building large models, such as in a deep network. You can pass some parts of the parameters using, sufficient factor because they are too big to be communicated, and you can also communicate some other parts, which are usually the early levels or layers of the network, which has a fewer parameters, to be a parameter server structure, and they get more efficiency, in doing this way. And then you basically combine the idea together, and that leads to, the speed up of a variety of existing big network models, such as the AlexNet, the Google LeNet, the VGG, and so forth, which all has anywhere from, a billion or more parameters, right? And again, they can be applied to, different models written in different languages, such as TensorFlow or in Caffe, PyTorch. Right. So that basically gives you a quick snapshot about how SysML, is leveraging both system knowledge and machine knowledge to design, better assistance. And also, this type of functions is modular. It can be encapsulated and implemented as an infrastructure outside of the program, so that they can be used to boost in the performance of a different type of models. Last but not least, every corner actually can be touched. Every stone can be touched. Even the programming language and the software framework, could still be innovated with knowledge from like machine learning. So I don't have time to dive deeper into that, but now, so we probably are now already sold to TensorFlow, right? When we are building deep learning models, what's the language you use? I guess TensorFlow, if right. Anybody use something else? PyTorch? Okay, good. They are the same, right? Are they? They are almost the same. Well, of course, they are different, right? They are different, but their fundamental principle is the same. Do you know what is that? They are or implementing a so-called data flow program, right? So that's the same, right? And the idea is that data flow is intuitive and direct from your model and from your data. Therefore, I can pre-compute all the gradients of every step in the back propagation, and also I can have a process or a schedule of the back propagation once your model is uploaded or implemented in TensorFlow, and then you let the whole thing to do by itself. That's actually very good because it applies to a large number of machine learning, deep learning models. Have any one of you tried applying TensorFlow to what we call dynamic networks? That the network has a different size depending on different data points. Have you done that before? Mm-hmm. Yeah, or maybe simply language application. You have languages of different sizes, different lengths. Have you ever done that? Or maybe language you do a parse tree, or you do a segmentation, right? This actually turns out to be hard. Or maybe even image of different sizes. You have 5 by 500 and 100 by 1,000 by 1,000. What do you do if you have that? I guess you pre-process and alternate into the same size, right? Yeah. Why you do that? Because TensorFlow and PyTorch intrinsically is a static fixed-sized model. Okay, you assume a template, you build a data flow program on that, and that's one template and a flow on that. And that template basically corresponds to the model structure and also the size. And if you have a different size in image, you all crop them or you just subsample them, whatever you need to get into the same size. If you have a different sentence length, then what you do is you maybe just do more. You stretch everything to be the same length, which is the longest sentences. And then for the shorter ones, you just paddle them with zeros and all that. Right? That's all you do. So this is what I call to be, you made a pair of shoes already, then you cut your feet to stuck into the shoe. Right? That's basically what's convenient and maybe even economical. But it's very painful. Right? Go ahead. Yes, it has now. Intrinsically, it is static, and the dynamic thing is allowing you to now compile a data flow program for every data point. Okay, that's a problem, right? Because if you look into the compilation time and the computing time of the TensorFlow, you actually will see that 80%, 90% of the time actually was not about back propagation. It's about computing that computer data flow graph. Now you have 1 million data points. They are all of different size, and you do that, right? So the very concept is based on a given graph. Therefore, you cannot bypass it, right? Okay, so that's TensorFlow. It's a program interface which was loved by other things, but now I point out a few things. Basically, it has some trouble in dealing with dynamic data. Okay, dynamic different image size or different sentence size and all that, or you just iterate this fixed sized model, as many times as the number of data points, and each time create a new data flow. That's the only way to bypass it. Okay, but now you know machine learning so well already, and after all, it is a graphical model with the structures, between different nodes. And one way we look at the structure is like this. We have a bird's eye view of the whole thing, and then there are data flows on that. Now, I invite you to imagine yourself become a tiny dwarf and sit even only on a particular node in the graph. What do you see? Your universe. You only see your neighbors. You only see data coming into me and data coming out to me. If I have not a data flow program, but the so-called Vertex program, where I only worry about the local configurations across all the models and all data points, then I have a different way of organizing my computing, right? So in fact, the data Vertex programming, in system is well known. Okay, it's actually used in many places. In fact, in many of the social media, your social network computation is a Vertex computation. They don't look at the entire graph, at least very often, in making your own computation, right? But this idea isn't used, in the deep network. So recently, there has been a new work published here between my group and a few other collaborators, which is now taking ML as a DL as a Vertex program. You literally just focus on how to implement these local functions, Vertex functions, okay, depending on the local configurations of the network. What you do is to again do a compiling, of all data points and the model, and your compilation now is built on every node, and to now carve out all the low configurations, and then you're going to repetitively compute it during the iteration when you do updates and learning. And that allows you a tighter and dynamic way of dealing with the data of different sizes. Okay, and so that basically offers you a alternative, over data flow program, for implementing deep network inference engine. Again, this is built on some knowledge of the graphic model, and therefore all these different structures can be easily accommodated. And there are they have some other more kind of advanced technique in doing memory management to more tightly couple. They invented something called a dynamic tensor, which allow you to store this kind of a local structure of different sizes more compactly into the memory, so that you can allow bigger models to be taken care of, by a modest machine. And here's a comparison of these different approaches. The green curve is the Vertex program. I believe the red curve is the original TensorFlow program. The blue one is called DyNet. It's a light version, focused on only parameter updates, but leaving the structure, as a one-time compilation, as in TensorFlow. So it's a semi kind of a dynamic program, a dynamic network input language, which gives some speed up. So you can see the comparison of these three over, models of different sizes and the data of different sizes and so forth. Okay, so I want to really close now. All I'm trying to say that AI is really beyond just algorithms and models. Okay, there are a lot of opportunities, tightly connect to your knowledge of the model and algorithm, which can make your job even better. And before I close, I want to say a few words about the so-called explainable AI. I think nowadays, there has been a lot of outcry, complaining many data in AI, application to be too mysterious and intransparent. With what I just described, for the whole semester and also in this class, I want to offer you again, maybe a more comprehensive way in the future to address explainability. First of all, I agree explainability is very important, but I want to also emphasize that explainability of the AI is not just about showing people the weights of the model and showing people a particular pathway inside the model that leads to a particular outcome and so forth. It's actually more than that. At least from what I just described, you can see that this process, data processing, model training, inference, and process deployments all influence the performance of the model. Okay, everything can be perfect, but if your data is dirty, you don't get answer. Or maybe data is not processed correctly, or everything is perfect, but your machine isn't working so nicely. You got a unfriendly neighbor which grabbed half of your machine on their program. Maybe your machine will do some asynchronous and incorrect results. Right? So you need to now look into the explainability at all these levels, so that you can really figure out what processor and what embedding and what particular treatment you did, in stripping information away from data or in preserving information within the data. And then in model, it's not just about model weights. It's also about in unsupervised learning, different type of boundaries, different type of bases, and different layers of and the framework that may be contributing to the outcome and to the the uniqueness or the specificity of the outcome, and also how data instances during inference trigger different parts of the model. Sometimes giving a explainable model is not important because different data points may trigger different subsets of the model to give an inference. Therefore, the inferential explainability is just as important as model explainability. So all this actually has to be explained. In fact, there are some latest work which allows so-called the model data-specific models to be produced. For every data points, you may be able to train a unique model only for its own prediction. And if you're interested, you can look into some of the papers that we post on the website. And lastly, but not least, you need to understand the system so that for an accident and for a mistake, you at least don't forget to check the system to see whether the contribution, the source of the error come from that part. Right? So these are giving you hopefully a more comprehensive overview about explainability. And I want to now close with a very quick summary. First, I want to repeat, I'm not such an optimist. I think the machine learning is still very early. We have a lot to do. There's nothing to worry that we run out of topic for our thesis work. Okay, there are a lot of unknown. We are probably here. We are not here yet. We are sort of here. Some models can be registered into a place in here and here, but not all of them. Only when you actually know the periodic table of machine learning elements, you know the outcome when you combine them together. That's how people actually study chemistry. You actually can predict the property of a compound from two ingredients if you know the atomic structures and everything in the periodic table. But in machine learning, sometimes we know a combination of algorithms outcome, sometimes we don't know. Therefore, a lot of work has to be done in here. And we're definitely not here. A chemical plant of AI doesn't exist because that's only possible when you know the whole periodic table and know predictively and certainly the outcome of different combination of innovations. So I think you can call it engineering, and isn't that above science? I think engineering is above science. You only need to finish this part before you go to the true engineering part, right? So with that, I think we are done with this semester. I want to close by saying that if our goal is to really push AI, of which a graphical model approach is one of the key technique foundations, it requires both a scientific process and also a sound engineering process. And hopefully, someday, with your work, we can turn AI into something as trivial as civil engineering or electrical engineering, where no physics professors is needed to fix a house and to wire a line in a building. Electricians with a high school degree is adequate. Right now, I think, of course, you guys with a PhD degree or master degree in computer science in AI are still in high demand. You need to do more important work down the road and leaving those assemblage, this part, hopefully, to the greater audience or practitioners of AIs. Okay, with that, I think I'm done with the entire lecture. Thank you for staying this far with me. Tomorrow we still have a presentation of the project. I really look forward to see your outcome. In the past, as I mentioned, many of the papers becomes the students' first major publication or become highly recognized results in major conferences, such as the NIPS conference, that Neurix conference that is coming in a few weeks. So I hope this project can prepare you a little bit better for that kind of adventure. Okay. All right, thank you very much. Okay.